of what fields are, and I'll hopefully come to the motivation of my work in the middle of my talk. And I have to say that as is the case of most things, I understand details only very superficially, so what I'm going to present will be very distilled version of definition of a field, but I will mention all the properties which I'll need in the constructions which I'm going to do. All right? By the way, can you hear me all right? Fine. So I will fix a natural number d. So this is a natural number. So there are different conventions. So in France, is 0 natural number or not? Yes, okay, fine. So no need to specify it. And I will speak about manifolds, but I will not be very specific what I mean by manifold. So it may be smooth manifold, it may be piecewise linear, whatever you want. It may be complex manifold. But anyway, having this fixed natural number d, I will say that I am given system of fields. If I am given for any manifold x, possibly with a boundary of dimension a set Cx that depends contrariantly on x, plus the following data. So if Z is a subset of a boundary of codimension 0, I have a functional restriction of a field from Cx to the field which I denote this way on the boundary. So this is one piece of data, and another piece of data is a gluing. So suppose that I am given manifold which is obtained from two manifolds by gluing along some part of a boundary, and I am given fields from these manifolds. Which restrict to the same field on the common piece of boundary. Then I have I have a gluing. I can glue these fields along the boundary, along the common piece of the boundary. So this will be a field on this union. So the picture is obvious. I mean, I have a manifold which is obtained from two manifolds, x prime, x2 prime, by gluing along some common piece of boundary, and I'm given field C prime, C2 prime here, which restrict to the same field on the common piece of boundary, and I may glue them together, and then all this gluing this way, and this gluing must be again functorial in almost obvious sense. So finally, let me introduce the notation. If Z is, as before, codimension 0 submanifold of a boundary, and little c is a field on Z, then I'll denote by Cx C a subset of fields from Cx such that F restricts to a given field C. Okay, I'm going to give you a couple of examples immediately. So you may wonder why I wrote this thing over there, repetitio mater studiorum. This is because, well, I'm not sure about the spelling, it's a long time, but because I gave the same talk in Nice, so for these who already listened to the talk, it's just recalling the things which I was explaining there. So what about examples? So the most, let's say, stupid example is I take as a fields on X just the maps from X to a fixed field B, a fixed set or space B. A little bit less simple-minded and actually physically meaning, I hope, is taken by Cx the set of equivalent classes of G bundles with connections over X. Yeah, I guess that electromagnetism is example with G U1. Yeah, but during my talk I will assume also the following thing, that if X is of maximal dimension, D plus 1 dimensional, then I assume that Cx is enriched over, well, in my talk, over, let's say, graded vector spaces. So none of these two examples are of this kind, but I'm going to give you immediately examples of which satisfy this enrichment property. So this is examples coming from D plus 1 categories with strong duality. Again, don't ask me what precisely this means. Examples are disk categories, such that D plus 1 morphisms are enriched over graded vector spaces. And I'm going to give you a couple of examples, actually 2 examples. All right, so interesting. Okay, so this is example of D is 0, which means that the maximal dimension of manifold will be 1. So what is my category with a strong duality? It is category C, which is just one category, which is enriched over vector spaces, and which has a kind of star adjunction from, let's say, CAB to CBA. So you may think of it as of C star algebra with several objects, if you want. Example is finitely dimensional vector spaces and with given basis and linear maps, therefore matrices, and then star will be just a junction of matrices. So if you have such a thing, then for dimension 0, for the points, so if dimension 0, if X is of dimension 0, meaning a point, so you decorate the point by objects of category C, by C0. So what are the fields on a manifold, one-dimensional manifold X? So one-dimensional manifold X is basically either interval or circle, if it is connected. So the fields, they consist of the following data. I'm given a triangulation, which is just division to intervals, and I'm given transversal orientation of endpoints of these intervals, and I decorate the intervals, the interiors of intervals by objects of category C, and I decorate the, let's say, the endpoints by morphisms, which point in the direction which is indicated by my transversal orientation, and I mod out by relation given by a junction, and this will be my fields. So this is very explicit, and you may play with it if you want. Let me give you an example of D1, which means that the maximum dimension of my manifold will be 2. So I just draw the local picture. So fields would consist of triangulation of a manifold X, such that the vertices of triangulation will be decorated by 2 morphisms. The edges of triangulation by 1 morphisms, and 2-dimensional regions by objects of a category. And I'm also given, as in the previous case, transversal orientation, which in case of edges is clear. So I know what is the left, what is the right side, right hand side. And as far as the vertex is considered, I'm given a division of adjacent edges into inputs and the outputs, which is indicated by this horizontal line. And there are, of course, some relations between these things. So, for instance, gamma would go from C to D, and alpha is a morphism, is a 2-morphism, which goes from F star G into delta star beta gamma, as indicated before, right? So this is a field for D is 2. And again, I mod out by the 2-dimensional of these relations. Okay? Any questions? Fine. So let me try to do something with the board. Okay. So now I'm slowly moving to one word in the title of my talk, namely to the blob. So what is a blob for me? So blob for me is just image in X is image of embedded standard. Okay, I assume, speaking about blobs, I was always assumed that X is of maximal dimension D plus 1, so image of embedded standard disk. Maybe I'll denote it by D this way or something like this. So, I mean, actually you already see some pictures over there, but I'll be more specific. So this is a blob for me. And then I need to speak about, I need to say what I mean by local relation. So what is local relation? This is a system U, okay, subspaces of fields on blobs. So this is a blob. Such that, all right, I already wrote it, dx is a blob in X. And C is a field on the boundary. So system of local relations is such a family indexed by blobs in X, which is ideal. It's an ideal. In kind of very interesting sense, namely what I want. Suppose that I have the following picture. I have, so this is my manifold X. I have blob D, let's say D, and inside I have another small blob D prime with a field C on the boundary of the blob, and another field, I don't know, D on the boundary of the big blob, and I am given field little u, which is from local relations of D prime and restrict to C, and then I have another field, u, let's say R, field R, which is now just a field on the complement on D minus D prime that restricts to C and D on the boundary. Then the condition of this being an ideal says that gluing of these two fields along C is local relation of the big thing. So I believe this is very nice. This is very nice thing, right? This is very nice thing. Geometric version of ideal. Fine. So now suppose that I'm given system of fields, I'm given local relations, then I can define AX as a quotient of fields on X. Remember that I am in the top dimension, so by my assumption it was enriched over vector spaces, modulo subspace, or let's say subspace generated by local relations. And this object is called scale module. And is it one of these topological quantum field invariants? People are playing with, right? Fine. So this is introduction, and now I'm going to tell you what the blob complex is, and then I will come to motivation of my work. So we have a field, we have local relation, we have a scale module. So what I can do is this. I can construct a blob complex. A blob complex, actually, this construction is not mine. It is due to Morrison and Walker. You can find citation in the paper which I put on the board. So what is it? So it is a complex, as the name suggests. So it is a complex B2 x B1 x B0 x. And okay, let me make a little experiment. No. It's interesting. I just want to lift. Okay, I give it up. So B0 x is just the fields on X. Remember, I am in enriched situation. I still need one of these boards, so nothing happens. Interesting. Oh, I don't know. well, actually, I'm going to erase this because I'm not going to use it anymore. So I'm going to erase at least this. So B0 is just the fields on X. So B1X is the following pieces of data. So it consists of a blob in X, field C on the boundary of the blob, D, and field R. This is a field from the complement, on the complement of D, well, with some boundary condition. I'll be very relaxed about boundary conditions, plus a local relation on the blob C. So basically what I have, this is my manifold X, I have a blob D, I have a local relation U inside, and I have an arbitrary field in the complement, only subject to a requirement that the restriction on the boundary of D coincide. So this is my B1, and what is my differential, which should take me to B0, to B0x. This just takes this couple U R into gluing over the boundary D R. Yeah. So if you just ponder a little bit, you will see immediately from this definition that H0 of blob complex is a scale module of X. So what about B2? So B2, now I'll just draw the picture. So B2 is a direct sum of spaces consisting of data of two different kinds. So the first kind of data is two blobs in M, two disjoint blobs in M, with a local relation inside, let's say U1, U2, and the arbitrary field in the complement. And the second component of B2 is the configuration where blobs are inside. So I have two blobs, I have a local relation in the small blob, I have some field in the complement in the middle blob, and then another field in the complement of a big blob. And what the differential does, so differential should take me into B1. So again, it has two parts. So it is D1 plus D2. So D1 part glues R with U1 along the boundary. So I'll be just with one blob and the field in the complementary local relation. And D2 does the same thing for U2. And in this case, again, differential has two parts. The first part glues R1 with a local location U. So because this is ideal, as I explained, now it becomes clear why I need this property. I'll get local relation in the blob and field in the complement, so I'm B1. And the second part of differential just glues these fields R2 and R1 together, and the result is arbitrary field plus little blob which is left, so I'm again in B1. Okay? And it should be clear now what the general principle of construction of blob complex is. So, for instance, so for instance, B3 X would have pieces of the following type. So you may have 3 disjoint blobs, or you may have blob 1, 2, and 3, or you can have 1, 2, well, okay, something like this, and so on. So the data will always consist of blobs which are either mutually disjoint or one the subset of interior of the other one, and there will be decoration by local relations and fields, which should be clear from this picture. So what I get is, as I say, a complex which is called blob complex and is due to Walker and Morrison, and the crucial property is that H0, as I mentioned, of this blob complex is a skein module of X. Very good. So now I may finally come to the motivation for my work. So I listened to the talk of Walker Morrison, of Kenyon Walker in Berkeley, and he was explaining this kind of definitions, and I realized that the picture resembles something which I know very well, namely the construction of 3 operad in the operatic category of graphs, except that instead of graphs I have a manifolds. So I realized that there must be something which I should know very well, and that it should fit into some general scheme. So the following question somehow appeared. This shows that this is kind of resolution of AX. The question which I asked, is it indeed a resolution in the sense we understand, namely, is the BX cofibrant or even free thing in some suitably defined category of I don't know what? So therefore, is indeed B star X kind of derived or homology of this thing, which is acyclic? Okay, so this B star X is kind of derived scale module. And I got actually 2 answers to this question. So where I am, yeah. Again, I need to erase something. Maybe I can try again. So nothing happens, interesting. No, this is not. No. It's simply beyond my abilities to operate this. Okay. So there are 2 types of answer to this question. Let's say the first one, semi-classical. That B star X is isomorphic to bar construction in the sense of Benoit Fraisse of a suitable colored operad, which is kind of colored version of little disk operad, but this is the approach which I'm not going to discuss. And the other answer is that B star X is quasi-isomorphic. It's quasi-isomorphic to again bar resolution of an operad over unary operadic category. So notice that while this was indeed a isomorphism, this was just quasi-isomorphism, and the relation between these two things is like between trees with levels and trees without levels. So there is very nice interpretation of this quasi-isomorphism, but of course I have no time to speak about it. And I will focus on this second approach because this should be also kind of advertisement for operadic categories, which is a notion which I invented with Markl Batanin, who was actually written as one of contributors to with Markl Batanin. Okay, so now I'm going to mention the most important features of operadic categories very briefly, and then tell you what this operad is. So where am I? Okay. Again, I need to erase this again because I don't dare to play a game with the board. Interesting, I feel that I know how to handle it, but somehow. Very good. So what is operadic category? So certainly it is a category. It is a category O, which is equipped with a functor to skeletal category of finite sets, namely finite ordinals. So this is one piece of data, this is a functor, and then another piece of data is the following. Whenever I am given a map morphism in this category S to T, such that, so this is notation for this functor, such that the value of this functor on the target is n, so we call it cardinality. So when cardinality of T is n, then I am given another object f1, fn, which we call fibers of f, So every morphism whose target is of cardinality n is equipped or comes together with n objects of category O, which we call fibers, and we wrote this fact using this symbol. So this, for us, this meant that F1 and are fibers of F. And of course, there are some axioms which these fibers should satisfy, and I will give you a very simple example in a minute. So I am given operatic categories. So obviously, I expect to have operads, notion of operad. So what is operad over O? What is operad over O? So this is a family P indexed by objects of O, and together with a structure operations which are indexed by morphisms, like this. And the structure operation goes from P of a target times very well. So this is a family in symmetric monoidal category. So this is a symmetric monoidal product. P F1 times P Fn So this is structure operations, and they must be associative in appropriate sense, and we also may or may not require some unitality. I would very much like to have another board. So this goes up fine. So far, so good. So far, so good. Guillotine. So examples. O is everyone's favorite category, delta finite ordinals and order preserving maps. Cardinality is inclusion into finite sets. So what are the fibers? So let me give you example. S is this ordinal and T is this ordinal. So 1, 2, 3, 4, 5, 6, 7, 1, 2, and F is the map which goes, for instance, like this. So this is F. So in the notation which is somewhere above, this is T and this is S. So fibers are by definition pullbacks, but I have to emphasize that they are actually typically the fibers in operatic categories are not pullbacks, but in this case they are indeed pullbacks. And so this is 4 and this is 3, right? And what is this structure operation? It goes from P2, okay, I have to be more precise, P2 times P3 times P4 and goes to P7. Yeah, and it is not very difficult to verify that operads over this category are precisely non-symmetric operad in presentation of Peter May. And example number 2, just very briefly, because it shows that the operatic category may have quite a different nature. O is a category of graphs. The cardinality of G is a set of vertices, morphisms are basically contractions. Okay, so ideologically, I am given graph S, I am given graph T, okay, and they have some vertices, and contraction means that some subgraph here is contracted to a vertex, let's say, number 1, then the graph that has been contracted is a fiber over this vertex. So these are fibers. But I have to warn you that this is very rough. We had spent with Markl about 2 weeks to figure out what are precisely the data of a graph. So there must be some orders of vertices of edges adjacent to each vertex and to edges adjacent to the legs of the graph. So indeed we spent quite a long time to understand what is it, and in one of the papers which we studied the category of graphs, there are like maybe 15 pages proving that this is indeed operadic category, which is just what we want. So it is deceivably simple, but in fact it's quite combinatory, quite involved combinatories behind. So what are operads? So again, operads, I must say, are something like hyperoperads in sense of Getzler and Kapranov, and we have a property that algebras over terminal operad of this type are modulo operad. But again, one has to be careful about various conventions. So the devil is in details, indeed, in this case. Very good. So I hope that this gives you some idea what operadic category is. And now, simplistic case is is unary. So we say that O is unary if cardinality of each object is precisely 1. So this looks quite simple. Therefore, what the fibers are, if I'm given a map F, it has only one fiber, F. What are operads? Operads, interesting. Operads are, as before, collection indexed by objects of O, and structure operations are gamma F going from PT times PF into PS. Something very simple. So one example, almost obvious one example. O is a terminal category, namely one object and one automorphism, namely the identity. Then, okay, fiber is again the only object that this category has, and O operads are associative algebras. Well, so in this sense, the theory of operadic categories involves all classical theory of associative algebras, if you want, but this is certainly not what was the motivation. The point is that the subcategory of unary operadic categories on one hand contains simple examples like this. On the other hand, it contains some very unexpected things like decollage, two single spaces, etc. So again, I can give you some references if you are interested. And namely, we will see the example coming from decollage. This will be precisely the category which I'll need to solve to answer my question. Very, very good. But let's stick to general case. So if I'm given operad over unary operadic category, my God, my heart almost stopped because I saw that I erased it. So I can define bar resolution, which is above. So this is over there. Fine. So what are the pieces beta n of this bar resolution? First of all, I consider towers Tn, which is towers of maps of these unary operadic categories. Given such a tower, I got sequence of fibers, F1 up to Fn, and F of this final alpha. Having this, I take tensor product which are denoted by Ptn, and beta n, the nth piece of this bar resolution, is direct sum over all isomorphism classes and so on and so on. It's kind of colimit, of course, over these Ptn's. Yeah. And precisely as a classical case of, I think, MacLean or other people from the 60s, this is a simplicial abelian group, and therefore there is an associative chain complex, and the associative chain complex is the bar resolution which I'm talking about. Yeah. Fine. So now, back about the general question, special question of what I can do with a blob complex, having this beautiful concept. As I say, the example of unary category, unary operadic category is decollage. So what I mean by this, if A is a small category, I may define, well, I don't know how to pronounce it, it comes from Grothendieck, I guess, or some French, definitely some French word. So this is a overall objects of A, and now I take comma categories A over A, so this is decollage. It can be described using the nerves as a cut in the top piece of this nerve maps. So it has also simplicial interpretation where I am, yeah. So this is decollage, and notice that if A has terminal object, then A embeds into this decollage of A just by interpreting any object A as a map, as a unique map to this terminal object. Yeah. So now the claim is that dA is unary operadic category. Very good, so what I need, I have objects, cardinality of each object is 1 because it must be unary, and I must say also what the fibers are. So what is a map in this decollage? So the map of object which is mapped from X to A into another object, let's say T from Y to the same A, is some F such that this diagram commutes, and I say that fiber, so this is F, and I say that fiber of F is all right, is this little f, which is now interpreted as an object of A over Y, which is subcategory of this decollage. So it's kind of tautological operatic category structure. Indeed, it's kind of free thing, but I'm not going to use this anyhow in my talk. Fine. Now, what is my category? I denote by blob the opposite category of blobs and inclusions. And So this is the opposite category of blobs and the inclusions. And it has a terminal object, namely the empty blob. And by capital blob, I denote the decollage of this category blob. So again, if you look up, you will see example of object of such category, big blob. Yeah, so you have inclusion from the D prime, from D2 prime 1 up to D2 prime 4, I guess, into D prime 1, D prime 2, D prime 3. This is inclusion. So in this category little blob, I have a map that goes in the opposite direction. Therefore, the corresponding object of decollage can be also described just by taking the complement. So you can equivalently describe this category big blob as a category with objects complement of blobs inside bigger blobs. Yeah. So this is my category, and now this is fine, I still have time. I can describe the operad having the property that bar resolution gives me the blob complex. Again, I'm putting some details under the rug because, again, the details are somehow important, but I hope that conception will be obvious. Fine, so so I'm going to define big blob operad F, like operad of fields. So what is operad over operatic category? It is collection indexed by objects of operatic category. So I must be able to say what F applied on this kind of pictures. So this sits in X. This is the object of big blob is. Yeah, and I say that this component of F consists of some field in the complement of these little blobs. There is nothing, no decoration of the blobs, of the little blobs, the small blobs themselves, plus if there are no small blobs inside a big blob, just local relation. So this is a component of operad F corresponding to this element of big blob. Yeah, and the operad structure is given in a fantastic way by gluing. So by the way, I didn't mention the boundary conditions, which are important, but only technically, not conceptually. So I didn't mention boundary conditions, they are there. So just to show you example of how this composition looks, I consider the following simple example. Okay. So these should be blobs. So this should be in the same X. So this is a map in big blob, and fiber is the map considered as a, I don't know what is it, as a category of decollage. So fiber is complement of the little blob in the big blob in this very particular case. So now I need to give you a composition in F. So what is F doing for this? So F is just a local relation on U. Well, this is a fiber, so what is F on the fiber? It is some just arbitrary field on the complement on the little blob inside the big blob, and I need to give you something here. So remember that this little blob is here, and what I give you is indeed gluing along the boundary of the little blob, which is because I'm working with local relations, namely ideal. The result is local relation. So I indeed, well, again, I just omitted a lot of details, and this is a very particular case, but I believe it's kind of obvious that this operad F of fields is defined precisely using the structure of fields, gluing, and so on and so on. And well, if you do the calculation, you will realize that the bar construction, which is already okay, it's kind of over there, is indeed quasi-isomorphic to the blob complex by Morrison and Walker. And to prove the isomorphism, you need very crucial one result of. Well, actually, this was this was all the result of Steve Schneider, but first did it in a more general form using homotopy, that these two things are quasi-isomorphic. Okay, then I think it's good time to start. Yeah, if you take finite sets, all finite sets, you'll get symmetric operad. I have actually one printout of this preprint which was there, so you can take it. I don't think there is any advantage. It's just a justification of another approach. And there are like two setups, like trees with levels and without levels. So this may also kind of explain the difference. So this was kind of neglected at the beginning of this operad theory, that there is some difference yet. There is a groupoid acting on it which is contractible. And now somehow it means that both points of view are have some justification by general theory. I don't know, frankly. Yeah, I probably had to make a disclaimer from the beginning that this interpretation of mine didn't bring anything in terms of concrete calculations. Okay, this is a good question. There is a calculation in paper by Morrison and Walker. They did it for a circle, and it is like 15 pages. So it's. I spent quite a long time to try to figure out, for instance, for two-dimensional things, because as an input data you have a category. So in one dimension this is just C-star algebra, but in the next dimension you have some category. I wasn't able to do it. But definitely, I mean, unless X is a disk, there is a higher homology. It is not acyclic, you know. So it's indeed like derived scale model, but. Maybe so. I mean, if you are masochistic enough, you may try to do it. You know, and this is a mixture of topology, you know, and in dimension 1 you are dividing in interval into little intervals, but in dimension 2 you have, you know, triangulations and all these things, you know, and you must be careful in which category you work, you know. Yeah. I don't know. This is another good question. I don't know. This is a very good question. Yeah, I don't know. I would expect, like in case of bar construction, to have something like operadic. But again, since besides some very trivial cases, there is no explicit calculation, you know. But this is a very good question, certainly. Yeah.
Like the thing